In this video, we're going to discuss how to set up a model in Adapt Builder for a two-way RC slab. And we're going to be using FloorPro, RC, and US units. If we expand this, we can see we don't need edge. That's used for multi-story analysis. And we don't need PTRC, which allows us to model the post-tensioning. We'll use US unit system, and I'll go ahead and say OK. Now, to create the model, we have different ways we could create a model. We could build a model in the program just using some of the native modeling tools. And we do have videos related to these options, other videos. We could also import a CAD file and then transform the CAD file, or we could use a Revit model, for example. And we're going to use the third option, which is just a Revit import to start our modeling. We have this Revit file. We're going to be importing level 10, and so we have the Adapt Revit link installed. We're going to go to the Analyze tab and select Export, and then I can export this data using this option here. And I've already created that file. So once that IMP file is created, I've saved it at a specific location on the computer. I'll go to Import, IMP, and I've saved this as a two-way IMP file. So I'll go ahead and save that, or select that, and we're going to import not all of the levels. We're just going to import level 10, which might be representative of a typical two-way slab in this model. There are no load cases or combinations, so we can go ahead and say OK. It tells us that there's a column that already exists, and I'll go to Zoom Extents. And the first thing we want to do, this is rotated 6 degrees, so I'm actually going to select this, and I'll go to Modify, and I'm going to rotate this model. So I'll select Snap to Endpoint, and we're going to rotate this model 6 degrees. We'll say Move. Okay, that was the wrong direction, so we'll do that again. We'll go back. And it actually needs to be -6. We'll do -12 degrees and say move. And it flags that repeating column again. So we'll go ahead and find that as well. You can see when we do that, all of the columns which were already rotated are now askew. So we need to actually rotate all of our columns by 6 degrees. And I'll select my columns. And typically, you wouldn't have to do this. I didn't have to actually rotate this model, but sometimes it's easier just to work with when it's in the orthogonal direction. We're going to go ahead to Home, select by type. We'll select our columns. And since we're modifying more than one component, I'm going to go to Modify, Selection. Okay, and under Column, the rotation angle we'll say is 6 degrees, or excuse me, 276. Let me just check a column. So that's 6. Actually needs to be 0. Let's try that again. I'll just window select this, modify selection, column. This should be 0. Okay, now they're aligned. So the rotation didn't realign the columns when we had rotated the slab. The next thing we're going to do is mesh this slab, just to see what kind of mesh is produced when we import this file directly from Revit. I'll go over to Analysis, Mesh, and the program will give me a warning saying there's 2 columns at the same position. And if you go to a 3D view using these view cubes at the bottom, you can see there's a column here that is duplicated. And I'll just select it once, delete. If I select it again and it's highlighted all red, that indicates that there's only one object at that location. If you want to default the color of a component that might have been flagged, we can go to Visibility, View Settings, and this is the central control panel for visibility in the model. There are ways to view things, other than this, but this is kind of the safety net for viewing inside of the program. So here we can go to Color Palette, and I'll go back to Column and reset the default display. Okay, we'll go ahead and save this. And let's go ahead and mesh again, so we shouldn't run into that error this time. And the mesh looks good. It's uniform. There's no clustering or densification of the mesh. There is one area where we have some very small elements that are elongated over on this uh, area between the edge of the opening and the slab edge. So that's one area you might want to modify. If we were to modify this in this model, what I would do is use this option to create a line. I want to snap on this endpoint using the snap to endpoint option, and then I'll use snap orthogonal, and I'll just create something like this. And then I can select that. I'll insert a couple of points here. I'm going to escape out of that, and then I'll grab that again and move these points using snap to intersection. Okay, now here I need another line, so do something like that. And again, I have snap orthogonal turned on, and now I can align that. I'll delete the opening, and in so doing, I'll save that, I'll remesh the structure, and we have our mesh shown as such. I'll mesh this at a bit higher size just so we can analyze this a little more quickly. So this is a 5-foot mesh, and we now have our model in place. Now if I was to analyze this just to test to see whether or not this analyzes, that's another step that you might want to take in validating the import from Revit. So I'm going to go to execute analysis for service total. We haven't added any load yet, so this is really just analyzing for the self weight automatically. I'll run the analysis. You'll notice that I didn't put any supports at the base of columns. The program will auto stabilize the slab, meaning it will create the supports automatically. So it's run the model. If I go to visibility, and over here in the results tree, I'm actually going to check under analysis. I'll use let's do the Z direction translation. And you can see we have a couple of hot spots of deflection, one being this corner and the other one being this edge. So it looks like there might be some components missing in that case. We're going to go ahead and fix that by just arbitrarily adding some components here. So if I add components, if I move components, if I adjust anything structurally in terms of the modeled objects, we need to remesh. So I'll just clear the mesh out, and I'm going to copy these two columns. I'll say Control C, Control V, and I'll just copy them here. Now if I wanted to offset them a specific distance, I could do something like so. I could take a measurement, or I could create a dimension also. And this is 26.4 feet. I'll take these and I'll modify by coordinates. I'm going to copy by coordinates in the positive X direction, 26.5, and we'll just say copy. Okay, and those are the copies. Now it said we had duplications again. Let's see if that's true here. Yes, that should be okay. Okay, so those will help support that area there, and then in this direction I'll just use Control C, Control V, and I'll just place those close to the slab edge here. Okay, now we're going to remesh, and I'll execute the analysis again for self-weight. And again, if we look at the slab deflection, we have about 1.5 inches of deflection down in this corner. I could also go to visibility under the rendered model. This is just a solid modeling viewer, and you can see if you turn on warping, you can see kind of a displaced shape of the deformation in that direction. There's kind of a hot spot over here also. I'll add another column there too, so we don't have these peak deflections where we're going to have severe locations. No, realistically, this could be the real model, but we're going to go ahead and make that modification also. I'll go back to analysis, clear out the mesh, and let me just copy this one. The reason that warning's coming up is because there's two columns below and above the slab. If I go to a side view, you can see everything's being leveled from, this is level 10, 11, 9, and so the program's flagging that when we copy it over, it's creating that flag, and then we have something going on here. Let's check that. Yeah, there's a duplication there also. That's the one that's being flagged. So, and then the last one we'll check, we'll leave this as a cantilever for this example. Go ahead and remesh, and then we'll execute one more time. The program assigns just the default characteristics to the concrete, which is called concrete 1. We can make modifications to material properties if needed. I'll show you where you can do that. Going back to visibility, I could also use the quick access tool here. And notice nothing is shown because I need to turn on the result first before I can look at that result in the rendering. Okay, we can also turn on, for example, this deformed shape, which gives a nice view of the deformation of all components in the model. Okay, we'll go ahead and close result display settings for now. I'm going to hide the mesh. So to do that, I could just go back to my default display, or I can go to view settings and turn off the shell elements like so. And under criteria, you can see we have our concrete assignment. Right here we're using 4,000 psi. We could add additional concrete materials if needed. We'll just leave this set as default. And then we have reinforcement defaults. Steel fiber and generic, we're going to be mainly using the first two. For the design code, we're going to select ACI 14. And then for the analysis and design options, we'll hit some of the rebar options later on in the tutorial. But under the analysis and design options, when the user analyzes the single level model, the program assumes some support conditions, and it's assuming roller support and rotationally fixed. Earlier I mentioned that when we analyze, the program auto-assigns supports. These are the supports it's auto-assigning, and after you before or after you analyze, you can actually go and under the model tab, you can view, using this visibility panel, I can view supports. So you can see supports at the base. If I double click, it's a fixed roller. You can modify this manually as a user. Let's assume that this one needs to be pinned, and I go ahead and select that. The program will retain user modification unless you delete that support. So if I wanted to generate the supports prior to analysis so I can review them, I could use this option to create supports. It creates supports based on the setting in analysis and design options, unless something was user modified, which in this case, this was set to a pin or hinged, so that user modification is retained by default. Okay, so loading, we're going to go ahead and select the outline of the slab, and I'm going to load. Under the loading tab, we have options for point, line, patch load, or wizards. Or we can import loads from an Excel file. We're going to use the wizards mainly for this example, and also this option for patch load. This tutorial is focused mainly on gravity loading, so there's also options for lateral loads which might apply to a global multi-level model in the program, and we're not going to get into this realm for this training. There are additional videos that talk more about lateral and global analysis. So we'll select the polygon. In this case, it's a slab, and we're going to use patch load wizard. I'll use 20 psf dead load, and if I select that slab again, I'll go back and use 50 psf live load. Graphically, the loads will appear. If we double click on those load entities, we can modify their properties. Each load is unique. In other words, you cannot assign different load cases to the same load entry. This is live load. It's 0.05. If I switch this to dead load, that means this actually becomes a dead load, not a live load. So it only stores one load case and one set of values for that load case for each entity. And then my dead load is here. This is 20 psf dead load. The load cases are stored under loading load case. You can see these are reserved load cases. One is superimposed dead load, the other is live load that's unreduced. The user can add additional loads using this button here, and these should go under general loads for a single level gravity model. Building loads only apply for a multi-level model. Load combinations. The program will fill a few default combinations based on your selection of design code. If you want to choose to add additional combos, you would have to use this option to add a combination, or you can clone combinations by right-click. Each combination has an analysis and design option type, so you could have service, strength. Service would mean the program would design that for minimum reinforcement. Strength is for ultimate level forces or actions in the design strips. Crack deflection would be used to check only the crack deflection of the slab. No code check might be used to see individual load case results, and then long term is used to check long term or predict long term deflection. We'll go ahead and add a few additional. I'm going to start with no code check, and we'll call this self weight. We have to have at least 4 characters in the name. We'll call this dead load, and we'll call that live load. And this might be to itemize the load cases just to see what the results are for each independent load case. Okay, we're going to also add crack deflection, but I'll use this option, add long-term deflection combo. It's going to ask me for the creep and shrinkage factor, so this is the ACI code allowable multiplier. We'll use 2. And the program will automatically include a sustained load case set to crack deflection, where we include 1/3 of the live load. The long term takes 1 plus the creep factor, which is 2, and it multiplies it by this crack deflection result. You could set up crack deflection combinations manually, combine combinations, and do different things with combos. This is just a very easy and quick way to produce a set of combos for this example. Okay, we'll select OK. I'm going to go to a plan view, and I'm going to add a bit more live load. We're going to go ahead and show, if we select add patch load, then the program will have us just place a polygon for loading within the slab region. Okay, so there's an additional load, and I'll call this a live load of 0.025, 25 psf. The loading is cumulative, so within this zone right here, I have 25 plus 50, because that 50 live load wraps around the entire slab. So here we have a total of 75 in this region. You can also add negative loads to offset loads in the program. For line loads, I'm going to map loads to this perimeter of the slab, and I'll use the line load wizard, and we'll say it's a dead load of 0.35 kips per foot. and that will create individual line loads that map to each slab segment. Okay. If you want to turn off the load view, you can use the show loads option, or you can go to visibility, view settings, and from the loads tab you can control the display of loads, including their dimensions. If I turn dimensions on, for example, the program will show me the magnitude of the loads for example, line loads. Let's do that again. You can see each line load is represented like so. Okay, so the next step is to generate strips. The program will by default automatically create middle strips. We're going to focus mainly on this little wing up here. We're not going to create strips for the entire model today, but we'll focus on this wing that sticks out. And we're going to create strips for both the X and the Y directions. So we're creating basically column frame lines like so. I'll actually do one along here. I'll stop it there. This is not going to be there. Or I could bring this across, down, and then out. So, and then I'll actually put what's called a splitter, which is just a boundary that the program will isolate this area to. Splitters can be used also to control the tributaries that are generated by the program. And we have other videos on more advanced uses of splitters. So we'll introduce the concept here, and then you can review those other videos on our YouTube channel for use of splitters. If you search keyword splitter, you should find a few more videos. I'll go now to floor design and create X direction support lines, and these support lines are used to generate the design strips. So again, this basically follows the column line, and I'm going to select this slab edge out here. I'll select the center of the column. I'm going to turn off the option for snap to nearest, and then I'll terminate it. Press enter or C on your keyboard. Here I'm actually just going to snap outside, and I'll come back and modify those when I'm done. And you could also copy these if needed. So we have several that are similar. I'll go ahead and just model all of them manually. If you make a mistake, you can use backspace to undo. And then right here, I'm going to just start this one maybe here. This will show the use of the splitter tool as it's currently constituted in the program. So if we have a support line that extends out of the slab, the reason I did that was just ease of use. I don't have to zoom in, turn snap to nearest on, and then come back and snap on that edge of the slab. I can just select these now and use snap perpendicular just to readjust those back to the edge of the slab. Okay, here we need to create a boundary, so we're going to create what's called a splitter, X direction splitter. The first splitter I'm just going to place straight across here. Let me try that again. I'll put a splitter there, and that bounds off this wing from down here. So in other words, the strips can't extend below that splitter. I'm also going to create a splitter at this endpoint that terminates inside of the slab region, and this allows me to create a boundary so the program can generate, this design strip in here and stop it at that boundary, and then over here this would actually extend all the way down. So we might actually want to put another splitter here just so this doesn't extend too far down. In reality, you would have support lines typically covering the entire slab, so you wouldn't need to add these long splitters to break it off. So we'll just add one more, something like like that. Okay, so let's go ahead now and do the Y direction. And to control the visibility of these, I'm going to go over to the strip results / visibility, and I'll turn off the support lines and splitters. I'll go to create Y direction, and I'll start at this column. And I'll start there. Typically, again, this would run down along the entire path of columns for the entire slab. But here again, we're just looking at one half of this slab. And then I'll just start this one maybe projected coordinate from that adjacent column. And again, I'm going to use a Y splitter in this case. So I'll take a point from this corner of slab. I'll just kind of piece this together. I'm actually going to do something like that. This slab corner and that slab corner act as boundaries. In criteria under analysis and design options, there's an option for the column and middle strips to be created automatically. The column strips are always created, but here the program will actually add middle strips to the generation of the support lines. Let me go ahead and delete these lines. So we have back in floor design, if I turn on the X also and the Y, we have X and Y support lines and splitters. I'll generate the sections and the tributaries now. And you can see there's some extension of this line all the way over into here. So that may require us to modify those splitters. Let's back up and I'll delete those. I'll turn back on my Y direction only. And let's go ahead and look at this. So you see there's a little gap there, but there's no splitters, so that's causing the leak of that tributary. I'll close this off by just extending it outside of the slab. And then I could readjust it perpendicular if needed, but generate these again. The same issue occurs. We'll go back and fix that one more time. I'm just going to add another splitter like so. I want to make sure this is snapped properly. Let me turn off the X direction support lines. I'll do this a little bit different. So I will create a straight splitter across there, and then this one we'll say it's from that corner down. See if that will bound off this tributary. Okay, so that does the trick there. Now we're ready to look at these directions independently. So if I go to the X direction, you can see the program. These are my column strips that I'm highlighting. And then the program basically adds in the middle strips where we don't have the generation of the column strips. So column, and then another column strip. If you wanted to create the manual or the middle strips manually, you would have to turn off the setting under criteria, this setting here, and then draw all of your support lines. So these are the X direction. We'll just go ahead with that. And then if we go to the opposite direction, this is the Y direction. So once our strips are established for the model, we can go ahead and design those sections. We're going to go back and analyze all of our combinations. When we analyze these, this block of settings here does not apply to a single level RC slab unless you have a global solution in place for like a multi-level model. So we're going to ignore that for this run. The uncracked usage case is just basically saying that there's no stiffness modifiers to any components. You can add stiffness modifiers to components by creating a usage case, but in this example we're not going to focus on that. And then we're going to leave these settings as they are. The program will auto-stabilize against in-plane translation. We'll go ahead and say OK. The next step, we have finite element results now. We're now going to go to floor design, and we've created our design strips. Now we're going to design the strips. And once the strips have been designed, we can now use the result viewer, which is initiated. It automatically will open. You can also go to analysis and use this result display settings, and it's shown down here also. So we can use this viewer to look at design strip results. And if we isolate, go back to floor design, and we isolate, for example, one direction, we can go to actions, for example, turn on bending moments. These are the bending moments along the strips. I could use the numerical display option to show all values. I could turn off and on, min-max values, scale the graphs, turn off the strip results or turn them on. There's different options in this block to view the results graphically. We can also look at axial force, shear, and so on. So this just shows me the actions for the selected load combination. In this case, it's set to service total. I'll just go to strength, dead on live, for example. And these are the bending moments for strength. Stresses are not reported for an RC slab. If I try to look at top or bottom, on design sections you cannot report the stress, but you could report them under slab actions. So we can look at actions and stresses. For example, top fiber along X, bottom fiber along X, and so on. You can use contours to look at stresses in this case. Okay, the next thing we'll look at, balance loading doesn't apply to this slab. This is for PT. This is mainly for PT. Deformations applies, so let's go ahead and look at deformations. If we look at the deflection, the program will take the worst case deflection in a span, take the span length over that deflection to produce this check. And whether or not the check is acceptable is based on the it's based on the setting. If we go to settings or under display here, we can base this on this maximum span deflection ratio. So this is helpful when you have column strips. Mainly for middle strips, what happens is the program takes the length of the span as being from end to end, so it's not as useful for a middle strip in this case because it's taking whatever the maximum deflection is for any section and taking the span length from here all the way to here, for example, dividing it by that value. So there are other ways to explore deflections, mainly in contour form, that we'll talk about once we look at crack deflection. Going back to the analysis results, the investigation is also useful. For moment capacity, the program will produce capacity curves for positive and negative moments. Purple is negative capacity, green is positive. You can also overlay the envelope of strength on top of this, and this reports the demand moments, the capacity, and also the demand capacity ratios for the model. So by looking at these curves, we can kind of tell where we have reserve capacity due to maybe minimum reinforcement, or where we have no reserve, where the demand capacity is 1. If you double click on any design cut and go to design sections, you can explore more information relative to that particular design cut. So this is a design cut that's rectangular. We have geometry, properties of the design sections, and then an accounting of the reinforcement. So the calculated rebar for this particular section is 4.4 inches, square inches. There's no base or user-defined rebar. There are no post-tensioning cables. And then under details, we show the reference from where that reinforcement is generated from. So this has a CG from the bottom of the design section upward by 1.5 inches. Below that is a design summary. This is being designed as a two-way RC slab, and then demand and capacity values. Each design strip is defined under the design tab as the design criteria. So back under the criteria menu, if we look, for example, at the rebar cover, for two-way slab, we're using a 1-inch rebar cover that could be modified by the user. The user can modify rebar size and material. For a two-way slab, we might change this to number 5s. You can also make settings for rebar roundup and rebar lengths, and that's more for just output and detailing of the reinforcement. If you wanted a user-defined rebar and add, for example, a mat of steel or isolated bars, you could go to rebar and model reinforcement in the slab, which would then be accounted for in the design. And then finally, to produce the rebar layout, I'll go back to my default display. We can select floor design, calculate the rebar plan for either the envelope or the envelope of strength or service, or individual combinations, and by doing so the program will produce the reinforcement in the slab. Notice it's blank down here because we haven't designed any rebar there, or we don't have any design strips there. So to control the display of the rebar, we can go to the rebar tab, display manager, and now I can isolate, for example, maybe I want to look at the X direction top bars only, and this gives me an output of those bars. To control the font size of these bars, we would then go to visibility. Remember, this is the view settings for everything. I'll go over here to rebar, and we could change the symbol or font size here. Maybe I want that to be a little smaller, maybe 15 inches. If we wanted to export the rebar to a CAD file or print it, print settings, this controls the font and coloring and appearance of the bars when we print, and the export settings controls the same when we export to a DWG or a DXF file. So there's different settings required for different outputs of the reinforcement. If you go to the reports menu, you can then generate reports for rebar that's generated from the structural model. You can go to design strips to look at design section forces, reinforcement, moment capacities, and so on. And then there's other reports for just basic general information, structural modeling reports, loading, punching shear we have not looked at. So the punching shear check after you analyze, let me go back to the default display. We can go back to floor design. This can actually happen once you analyze. You can execute the punching shear, and the program will graphically show results for punching shear. Now, this result display settings is upcoming this month in the program. Version 2018.0, which is our current commercial release. As of today, the user can control the output in this bank of tools under the floor design ribbon. So what you're seeing is actually a sneak peek of what the program will produce once it's released again this month. Here we can look at the stress ratio. This just color codes the stress ratio. You can also look at stress ratios here. These are not applicable. These columns are not being checked for punching shear for some reason. I'm not sure why, but I have to look at that. And then it would show the condition of the columns whether they're interior, edge, or corner, and it color codes that. And then finally, reinforcement would be shown using this option. This is all graphical reporting. You can also use the tabular reports under the punching shear menu. So once the reinforcement has been designed, we can check the crack deflection. So that's the final step here is we'll go to analysis, run the crack deflection check, and this will run through another process of analyzing the structure. This crack deflection check, maybe the output is not, let's say, complete, only because we haven't calculated rebar in this zone. So after the crack deflection check has been run, if we go to the slab deformation under the Z direction, we're going to go to loads, and for crack deflection we have the deflection assuming I gross and the deflection assuming I effective, and this would be the cracked deflection. So if we look at the sustained deflection, the maximum sustained deflection in this zone here, let me just change the range. I'll change this to label it every, let's say, one contour. And you can see here it's 0.65 up to 1 inch. If I go back and check the crack solution, the program will show where that cracking exists, and there's clearly a difference between the results if the slab is cracked. Under the analysis tab, there are ways also to check the cracking in the slab. So under actions, we can check the reduced rotational stiffness about X or about Y for a crack deflection combination. So in this case, it looks like the slab has not cracked. If these contours are identical, then you're not going to get any result for the cracked or the reduced rotational stiffness. That will conclude this video tutorial. If you have questions or would like to receive the model we've been looking at, please contact us at support@adaptsoft.com. Thank you.